Plunging through a cluster at 1,000 to 2,000 kilometers per second, a spiral meets the headwind of the intracluster medium and the pressure term ρv superscript 2 outmuscles the galaxy's own grip on its gas. The disk's cold reservoir peels back, first at the outskirts where gravity is weakest, then inward as the bow shock and shear build. Magnetic fields drape around the leading edge, Kelvin, Helmholtz billows roll along the interface, and long, filamentary wakes stream behind like tentacles. Along those filaments, knots ignite where stripped clouds are briefly compressed, H-alpha beads trace pockets of starbirth that will fade once the fuel thins. Metallicity gradients flatten as if a spoon stirred the disk, the warm halo collapses, the circumgalactic pantry is gone, and inside-out quenching follows. The stripped creature looks like a jellyfish only for a while, in reality it is a city losing its aqueducts. Without the inflow that once fed molecular clouds, the star-forming engine sputters. Radiation from newborn clusters and the X-ray bath of the cluster itself harden the spectrum that bathes every system within. The milieu is not merely photogenic, it is erosive. Planetary systems orbiting their host stars ride through this gale with stellar gravity as their seatbelt, but their climate control is rewired by the environment. Protoplanetary material around young stars is truncated, older systems lose shielding as the interstellar neighborhood thins and becomes hotter, making cosmic rays and hard UV more penetrating. Bow shocks form ahead of stellar winds, magnetospheres are compressed, sputtering and charge exchange chip at the top of atmospheres. Where high-energy photons flood upper layers, hydrodynamic blow-off can take hold, energy-limited escape carries light gases away, dragging heavier species when heating is intense enough. Hydrogen leaks first, oceans become a source for the sky as sunlight splits water and the lighter partner drifts into space. Oxygen and oxidized minerals remain, a deceptive residue that can mimic a biosignature while signaling only that hydrogen was lost faster than chemistry could bury the surplus. With each pericenter passage through the cluster's dense core, the flux spikes, the loss ticks upward, and the clock on habitability advances. As the host's gas disk is shaved down and then stripped outright, replenishment pathways for volatiles close. Cometary traffic from the outskirts dwindles because the outer reservoirs were the first to be torn away. Clouds that would have seeded rains and moderated climates never form. Planets that might have balanced on the line between blue and brown pivot toward aridity. Seawater concentrated into brines leaves salt flats where tides once ran, evaporite stack like geologic ledgers of a vanishing hydrosphere. Iron-rich dust, scoured from desiccating soils and rusted by the leftover oxygen, turns the air into a red veil that can lift for weeks, then fall in ochre drifts. Mountain snowlines retreat and disappear as greenhouse cycling first intensifies and then stalls when the working fluids are gone. On tidally locked worlds around small stars, nightside CO2 frost caps grow and shrink with seasons that are now driven more by dust opacity than by water. On faster rotators, global storms resemble a Mars scaled up, deep convective chimneys at the equator, planetary-wide dust lanes, lightning that crackles through powder-dry skies where rain no longer closes the loop. The same tails that glowed with newborn clusters become laboratories of erosion. Massive stars in the wakes pour out Lyman continuum photons and winds that act like sandblasters on exposed atmospheres in their light cones. Cosmic rays from supernovae within the tentacles lace through planetary magnetospheres, generating auroral ovals that are beautiful and expensive in terms of chemistry. Nitrates accumulate, ozone layers are punched and repaired and punched again. Over millions of years, what began as ecological stress hardens into a new geologic era. Rivers carve no new deltas, only dust streaks. Basins that once held seas become bas-reliefs of polygonal mud cracks and shorelines etched into stone. Silicate weathering, the thermostat of temperate worlds, slows to a crawl because there is neither fresh rock exposed by rainfall nor enough liquid to carry ions to the basins. Tectonics, if present, keeps moving continents, But in vain. The water cycle that made mountains green is now a memory lodged in fluid inclusions and in the isotopes of the last stubborn hydrates. Outside in quenching of the host and inside-out desiccation of its worlds rhyme with the same cause. When supply chains of cold gas are severed, stars stop forming and seas stop cycling. The galactic metropolis that flashed its jellyfish filaments across the cluster sky leaves behind a quieter, redder disk, a population of aging suns, and an archipelago of deserts revolving in orderly silence. Telescopes would read this history as a pattern: truncated gas disks, suppressed star formation rates, hard radiation fields, and exoplanet atmospheres trending thin, oxidized, and mineral-tinted. The image is not dystopian, it is instructive. Clusters are weather systems, and weather writes landscapes across every scale. In the same way that a single sand grain remembers the wind that moved it, a dune remembers a season, and a desert remembers a climate, a dead sea on a distant world remembers the day its galaxy grew tentacles and the sky began to bleed. Cluster weather is patchy rather than constant, so the scouring comes in pulses. As the host sweeps through cold fronts and merger-driven shocks, ram pressure spikes and ebbs, tails kink, then re-straighten, eddies in the wake alternately compress and erode clumps. Thermal conduction tries to evaporate the stripped clouds while radiative cooling fights back. Viscosity and magnetic draping suppress some instabilities and amplify others. In a single orbit, hundreds of millions of years, the galaxy can pass from a bright, knot-studded comet to a barer, redder disk with only a faint afterimage of its former supply lines. In the nucleus, asymmetric torques and pressure gradients funnel what little gas remains inward, igniting accretion onto the central black hole. Jets and ionization cones carve through the already thinned medium and add a hard, time-variable glow to the radiation budget seen by every solar system downrange. The same flow that tore away the pantry also switched on a lighthouse that bakes the shoreline. Around individual stars, astrospheres shrink because external pressure rises. Where the stellar wind once inflated a roomy bubble, the intracluster gas presses closer, termination shocks move inward, neutral atoms of the surrounding medium leak into the heliosphere and seed pickup ions that change the chemistry of the wind itself. Magnetospheres of planets are squeezed and more tightly coupled to the upstream flow, current systems strengthen, auroral ovals widen. Charged particles find shorter, more direct paths to the upper atmosphere. Every magnetotail becomes a windsock that snaps under gusts from cluster weather rather than only from its parent star's moods. On worlds with thin shields, non-thermal escape joins thermal escape, sputtering, ion pickup, and polar outflows nibble at the top of the air even when sunlight is low. On hot dayside hemispheres of close-in planets, helium triplet absorption at 1083 nanometers would deepen as blown-off gas forms a cometary shroud, sodium lines weaken because alkalis ionize. Transit spectra would show a dryness that is hard to mistake, muted water bands at 1.4 micrometers and 6 micrometers, strong CO2 at 4.3 micrometers, excess O2 collision features and ozone that together signal oxygen without oceans to balance it. CO alongside O2 would be the telltale of photochemistry unconstrained by a hydrological cycle, a mirror of oxidation, not metabolism. Volatile logistics fail from the outside first. Kuiper belt analogs and wide Oort-like clouds are the earliest casualties. Their weakly bound comets are stripped into the intracluster light or ground down into diffuse dust, so late deliveries of water to the inner system all but cease. The reservoirs that once rained small corrections onto climate become a diaspora of grains reddening the cluster core. Inner asteroids survive but run dry, impacts deliver heat, not hydration. With every million years, the carbonates and hydrates that locked away earlier atmospheres record declining exchange with the sky. Volcanoes continue to write in basalt and sulfur where interior heat allows, but the handwriting becomes spidery as volatile fluxes drop. Some planets drift into a CO2-dominated greenhouse that ends not in steam but in stagnation. Others overshoot into high-albedo dust eras where reflected light cools the surface until the dust lifts again, a chaotic dance whose period is set by storm physics rather than by oceans. Milankovitch-like cycles persist, but their expression is filtered through dust opacity and thin air thermodynamics. The last rains are local, convective, and bitter. They etch tree-ring patterns in evaporite terraces and then stop. Not every world succumbs equally. Massive super-Earths with deep gravity wells clutch their air and become pressure-cooked deserts with tropospheres thick enough to move heat but starved of water to move life. Subneptunes shed their hydrogen skins and step down the mass radius diagram toward rocky cores, their transition accelerated by the added EUV and by the shrunken astrosphere that no longer buffers particles. Tidally locked planets around cool dwarfs keep permafrost on the night side long after the day side has gone copper and ochre. Katabatic winds spill glacial air into basins, carving dunes that march under a thin sun. Icy moons fare better underground than on the surface. Sputtering scours their exteriors, but pressure and radionuclides can sustain brine oceans behind kilometers of ice, a last refuge where chemistry remembers how to be busy. These enclaves are durable but isolated, like aquifers beneath a continent that has forgotten rivers. From afar, a quenched disk with tentacular scars would broadcast its planetary census statistically. Thermal phase curves of hot, thin-aired worlds show brutal day-night contrasts. Light curves of temperate planets acquire storm season flicker as dust lifts and settles. Polarimetric slopes steepen because fine particulates dominate scattering. In transmission, water bands fade across many targets in the same neighborhood, while oxygen dimers and sulfur aerosols rise, an ecological signature written at the scale of an environment, not a species. Direct imaging with future coronagraphs will find continents that are too bright and too steady, the glint of seas absent even when geometry is favorable. Spectral maps of intracluster filaments will correlate hardened radiation fields with the driest planets, drawing a weather chart whose isobars span hundreds of kiloparsecs. The physics is sober, but the narrative is not defeat. Clusters are apprenticeships in scarcity. Civilizations, if they arise before the last rains end, would learn to husband volatiles, to roof entire valleys against dust, to quarry ice from shadowed craters and pipe it like a second atmosphere, to print magnetospheres around fragile worlds with loops of current hung in the sky. They would learn to treat comets as livestock, herded inward from what remains of the outskirts, or cultivated in situ by outgassing black rock. They would also learn to read the large-scale barometer, not just the orbit around a star, but the orbit of a star around a galaxy that has grown tails. Worlds become deserts under a redder sky because supply chains broke. Supply chains can be rebuilt, locally and temporarily, by minds that understand both chemistry and weather that stretches between galaxies. A fossil shoreline is a warning, but it is also a ruler. It measures what was lost and what must be replaced if seas are to return. Over longer arcs of time, the morphology finishes the sentence the environment began. What started as a blue spiral with gas-rich arms becomes a smoother, lensy disk, the kind astronomers file as an S0, its star formation rate dialed down to a whisper while old giants dominate the light. The criterion that decided its fate was simple and brutal. When the headwind's ram pressure exceeded the galaxy's anchoring gravity per unit area, layers of the interstellar medium could no longer stay bound. The threshold was crossed first in the outskirts, then marched inward as orbits carried the disk through denser, hotter lanes of the cluster. Pre-processing in groups often primed the victim before it ever met the main storm. Harassment, tides, and starvation had already thinned the pantry, so the tentacles were as much diagnosis as outcome. In the wake, dust grains charged by ultraviolet light and plasma impacts struggled to survive, sputtering lifetimes shortened, coagulation stalled, and what remained was lofted into the intracluster light as a cinnamon haze that reddened the space between galaxies. The central engine was not a bystander. As residual gas funneled inward under torques and pressure gradients, accretion switched on in fits and starts, and each episode sent out cones of hard photons and, sometimes, narrow jets. Those lanterns cut through the already rarefied medium and set chemical clocks in planetary skies. Methane fell under relentless photolysis, nitrous oxide was whittled away faster than biology could plausibly replace in a thin-air world, chlorine chemistry, fed by evaporites and perchlorates, produced hazes that raised albedos and cooled surfaces even as the greenhouse shifted from water to carbon dioxide. As oxygen accumulated not as a breath but as an echo of lost hydrogen, O2 collision pairs etched dimer features into transmission spectra. False positives for life multiplied in a neighborhood predisposed to dryness. Geology pivoted to wind. With hydrology retiring, Aeolian physics wrote the landscapes, saltating grains carved yardongs from friable rock, dunes migrated in broad, low-slung rivers of sand, electrical double layers built along dust plumes, and discharges stitched the skies with dry lightning that manufactured nitrates without rain to wash them to sea. Silicate weathering slowed until it became a boundary layer phenomenon in rare fogs over briny pans. Carbonate platforms, once buffers in a lively carbon cycle, stood exposed as monuments to the time when acid-base chemistry had a partner in precipitation. Isotopes kept the ledger, D/H ratios in any remaining waters trend high, 38 AR/36 AR drifts upward, and noble gases grow fractionated as the lightest isotopes find the escape hatch first. In drill cores on such planets, if anyone ever collects them, fluid inclusions would bracket the retreat of the seas with heartbreaking precision, salinity climbing, redox potential shifting, sulfates and chlorides asserting themselves where once there had been carbonates and clays. The diversity of outcomes still mattered. High-gravity super-Earths held on to dense atmospheres that pressed deserts beneath kilometers of air, moving heat efficiently but unable to return water once it had been photolized and bled away. Mini-Neptunes, especially those close to their suns, shed their envelopes faster under elevated EUV, stepping down toward rocky cores that inherit whatever volatiles were left in their mantles. Tidally locked worlds around cool stars became two-tone planets, copper daylight hemispheres under permanent dust canopies and nightsides where permafrost survived in shadowed basins, fed by faint vapor transport across the terminator. Icy moons, battered on the surface by sputtering and micrometeoroids, retreated into themselves. Brine oceans persisted beneath thick lids, warmed by radiogenic decay and tidal flexing, a stubborn chemistry class continuing after the school above closed. Rogue planets, shaken loose by cluster tides and close passages, drifted into the intracluster medium where whatever air they carried would condense and freeze unless they were wrapped in deep hydrogen blankets that could trap geothermal heat. The cluster did not only make deserts, it curated a cabinet of extreme habitats whose common trait was thrift. From an observatory's standpoint, the signal became a demographic gradient more than a single spectacular case study. In regions where jellyfish tails gleamed, exoplanet surveys would find suppressed water features across many temperate candidates and a bias toward thin or oxidized atmospheres. Phase curves with sharp day-night contrasts would outnumber those with gentle slopes. Albedo maps would show continents that were too bright for too long. Spectra would lean into CO2 at 4.3 micrometers and 15 micrometers, show enhanced O4 around 0.63, 1.06, and 1.27 micrometers, and display sulfur aerosols whose broad blue to UV scattering signatures hinted at volcanism working with dry air. Helium at 1083 nanometers would flare in escaping envelopes, and sodium and potassium lines would fluctuate under variable ionization from passing through hard radiation cones. Polarimetry would find telltale forward scattering peaks from fine dust, and time domain measurements would catch global dust seasons that rose and collapsed on chaotic schedules set by storm physics rather than monsoons. If, despite all this, life appeared early enough, it would adapt its metabolism to scarcity and to oxidants. Phototrophs, if they ever existed on the surface, would retreat underground or into endolithic niches, leaving pigments that peak not at ocean-friendly wavelengths but where dust and thin air still let photons through. Chemotrophs would haunt brine pockets and evaporite margins, cycling halogens and sulfur in tight loops. The biosphere's footprint in the atmosphere would be small and twitchy, hard to catch, easy to confuse with abiotic production, yet locally decisive. The lesson for a searching telescope would be methodological humility. In harsh neighborhoods, life, deserts, and false positives rhyme, so the diagnosis must be made with ensembles, with context maps of radiation, with cross-correlations between galactic weather and planetary spectra. There is, however, a coda to the stripping story. Orbits do not always dive forever, some galaxies bounce. Backsplash trajectories carry gas-poor disks back toward the outskirts where the intracluster medium thins and the headwind slackens. If filaments feeding the cluster remain accessible and if the halo has not been completely scoured, trickles of cold gas can rain back through thermal instabilities, condensing where turbulence seeds density peaks. Rejuvenation is rarely dramatic, but it is not fiction. Rings of star formation can light briefly in systems that had been filed as retired. On planetary scales, that doesn't refill oceans, but it can modestly re-wet skies where mantle outgassing continues and cometary fragments still graze the inner system. The grand desert is not perfectly permanent, it just has inertia. Against that inertia, technologies could act as local weather, mirrors in orbit to push climate equilibria, electromagnetic shields to fatten magnetospheres, pipelines from cold traps and crater shadows to valley floors, comet farms tended in the dim outskirts and steered inward like rain on schedule. In a place where a galaxy once grew tentacles and shed its lifeblood into the wind, the difference between a fossil shoreline and a living sea may eventually be the will and patience to reverse, at small scales, the physics that made deserts at large ones. In numbers the rule is plain. When the headwind's pressure ICM v superscript 2 overtakes the restoring force per unit area, roughly 2 pi g sigma star operator gas, layers lift and flow. Cluster cores offer ICM of 1010 superscript 3 cm superscript 3, temperatures of 1010 K, and orbital speeds near 1000 to 2000 km s superscript 1. The product is enough to unbutton a disk in tens to hundreds of mir, leaving filaments that can stretch 50 to 100 kiloparsecs before they fade. In those wakes, magnetic draping raises the alphane speed and stabilizes some surfaces while others shred. Effective viscosity is debated but never irrelevant. Turbulence seeds cold clumps that briefly defy evaporation. A few knots turn into compact, fast-moving fireballs of stars that will orbit as orphans when the gas is gone. What looks like ornamental streamers is a conveyor belt of supply lines being carried into the void. For planets, the timeline is staggered. Atmospheres respond on photochemical and escape timescales, years to megayears, long before continents can answer. Energy-limited escape rates scale with EUV flux and planetary radius over mass. Add non-thermal channels under compressed magnetospheres and the ledger tilts further. Helium 1083 nanometers absorption deepens in outflowing coronas, sodium and potassium lines jitter with ionization fronts, water vapor bands flatten when the hydrological engine starves. A world that once showed rotating glints from seas develops light curves dominated by dust opacity and albedo swings. Phase curves sharpen into steep day-night contrasts as thin air and dust curtains decouple hemispheres. If you stack spectra for dozens of temperate candidates in a jellyfish's neighborhood, you read the same chorus: CO2 steady and strong, O2 dimers too prominent for comfort, H2O muted, sulfur aerosols broadening the blue. It is a population signal of deserts written by a galactic wind. Dust becomes the author of landscapes and skies. Grain charging under UV and plasma sets the sign and magnitude of electrostatic forces, controlling saltation thresholds and lofting efficiencies. Once aloft, Finds raise the effective planetary albedo while cooling the ground, but they also warm the air if absorption is strong. The vertical temperature profile tips toward inversions that cap convection. Lightning grows from friction and double layers rather than moist updrafts. Nitrates accumulate without rain, a surface fertilizer with no farmer. Silicate weathering, the slow thermostat of climate, contracts to rare fog events, confined to cold traps and valley bottoms where brines can briefly wick and react. Carbonate and clay assemblages freeze a chronology. Early layers rich in hydrated minerals and low D/H give way upward to sulfates, perchlorates, and heavy water signatures. Noble gases fractionate as the escape valve preferentially admits the lightest isotopes. Even without fossils, the rock remembers the retreat. Not all atmospheres thin, some thicken into pressure deserts. Super-Earths hang on to heavy, dry skins that move heat efficiently but cannot resurrect oceans once hydrogen is gone. Their skies become CO2-rich with trace CO, O2, and O3 set by photochemistry, and clouds, where they exist, are sulfate hazes or lofted dust rather than water. Mini-Neptunes near their stars slide down the mass radius plane as cluster-enhanced EUV trims their envelopes. Some halt as hot, dense rocks with residual steam in their mantles, others as iron-heavy remnants that glow dull red at dusk. Around cool dwarfs, tidally locked planets grow copper daylight hemispheres under permanent dust veils and nightsides that hoard ice in shadowed basins. Cold, dense air spills downslope as katabatic winds that sculpt dunes into amphitheaters. Icy moons fare best in silence, sputtering skins above, brine oceans below, chemistry warmed by radionuclides and tidal strains, a private weather powered by geology rather than sky. The host's nucleus, when it wakes, draws lines across these fates. Ionization cones and jets carve hard-edged sectors where EUV and particles spike by orders of magnitude. Planetary systems that drift through those beams during a pericenter epoch endure punctuated losses. Helium tails brighten, ozone columns wobble, and upper atmospheres acquire hot layers that speed escape. Outside the cones the milieu remains harsh but steadier. Inside, it is a kiln. Over an orbital gigayear, a star can sample both regimes several times, writing alternating stripes of loss in any surviving climate archive. On the scale of a cluster map, you can cross-correlate AGN duty cycles with waterband suppression in exoplanet ensembles and recover a weather chart whose isobars are radiation fields. Simulations close the loop. Cosmological MHD runs of clusters resolve RAM pressure, draping, and multiphase condensation. Embedded galaxy models track the criterion radius marching inward. Nested climate models translate external fluxes and particle spectra into escape rates and dust season statistics. Feed those into forward models of spectra and light curves, and you get predictions you can actually compare. The fraction of temperate planets with water bands below a threshold as a function of cluster-centric distance, the distribution of helium line depths near jellyfish wakes, the polarimetric slope as a tracer of fine dust on worlds near strip tails. The hypothesis becomes testable not with a single poster child but with demographics. There are edge cases that complicate the picture in instructive ways. Backsplash galaxies that have already been stripped once can drift back to the outskirts. If their halos still seed thermal instabilities, drizzle of cold gas can restart star formation in rings or lenses. That is too little to refill oceans, but it can fatten thin skies where volcanic outgassing continues. Group infall preprocesses some victims so severely that by the time they meet the main headwind there is little left to strip, deserts by inertia as much as by weather. Conversely, a massive, compact disk with high sigma star operator can keep its inner gas longer, feeding an AGN that intermittently overpressurizes the remaining ISM and drives outflows in directions the wind had not chosen, a crosswind within the wind. Planetary outcomes mirror this variability. Rare refugia under thick air, caves with brines beneath evaporite caps, crater shadows that collect frost each winter and briefly run rivulets under a thin sun. If mines arise before the hydrological clock hits zero, engineering can bend the curves locally. Electromagnetic shields stationed upstream can swell magnetospheres and cut particle-driven loss. Sunshades and mirrors can push radiative equilibria back toward condensation. Ablative dust launched during peak storm seasons can break feedback loops by seeding larger grains that settle faster. Volatiles reimport from cold traps, crater shadows, and remnant comets can be plumbed like a second atmosphere, circulated through closed basins to restart a minimal water cycle. The energy budget is demanding but not absurd for a civilization that has already learned to live with dust. The hardest lesson is scale. The same physics that quenched a galaxy starves a planet, so solutions must respect both the small and the large weather, the teleconnections from cluster shocks to dune crests. From a distance the story reduces to a simple equivalence: jellyfish galaxies are supply chains snapping in public, desert planets are the invoices stamped, insufficient funds. Tales are not just pretty, they are receipts fluttering in a hot wind, itemizing what was carried away. Read enough of them, and you can predict the color of dunes under alien suns, the chemistry of thin skies, the odds that a transmission spectrum's oxygen is breath or echo. And if you ever walk across one of those shores where waves no longer come, the polygon cracks and salt crystals under your boots will be telling the same tale the cluster told, that gravity, pressure, radiation, and time can remake a blue world into a memory, and that memory, in rock and light, is precise enough to navigate by. When supply collapses, even color changes. Skies over desiccating worlds turn butterscotch near noon and copper at dusk as submicron silicates take over the scattering budget and push blue light out of the air. The horizon glows longer because dust holds sunlight after the star has set, yet the twilight is mute because aerosols suppress the rainbow signatures that water once made. Daytime convection grows tall, not wet. Columns of hot, dusty air rise like chimneys, capped by inversions that trap heat aloft and leave the ground oddly cool until the sun steepens. Dust devils stitch black lines across dry pans, their cores electrified by triboelectric charging that builds double layers and throws miniature bolts into the haze. Yardongs, wind-carved fins, lean in the prevailing direction like frozen flags. Where brines briefly emerge, they crawl rather than flow, advancing with capillary fingers through salt crusts that crunch underfoot and preserve footprints for years. The chemistry of such places is not quiet, it is busy at low tide. Perchlorates, sulfates, and nitrates trade oxygen, iron flips valence in thin films, volcanic glass hydrates just enough to record humidity cycles and then dehydrates again, clocking seasons that have no rain. Deep below, water is not gone so much as collateralized. It sits in crystal lattices as hydroxyls, bound in clays and serpentinites, locked behind activation energies that only metamorphism or volcanism will pay. Mantle outgassing continues on planets with warm interiors, but what climbs is a thin stipend, not a salary. CO2 and SO2 in puffs, trace H2 and H2O that frost the night before photolysis can promote them. Basaltic plains disgorge darker sheets that cool under a dust fall before they can weather to the reds and ochres above, creating spectral two-tone terrains whose albedo jumps are large enough to modulate unresolved light curves. In caves, chemistry holds on longer. Drip points under cap rocks feed stalactites of halite and thenardite instead of calcite, inclusions trap bubbles whose gases will one day read like a cardiogram of the dying sky, oxygen rising, hydrogen vanishing, noble gases fractionating in slow, elegant arcs. Microbes, if present, would write their signatures as isotopic biases in sulfur and nitrogen along evaporite margins, faint against the louder signal of photochemistry but still legible where energy is steady and ultraviolet light is thin. Across the cluster the same motifs repeat with local accents. In outskirts where densities are lower, stripping is partial and strangulation dominates, Star formation fades by starvation rather than by shock, so planetary climates decline more slowly, with lingering lakes that turn to salt steppes over tens of millions of years. In intermediate radii, pre-processed galaxies fall in with their pantries already half empty, their tails are shorter, their deserts more advanced. Near the core, full jellyfish flourish and then wither, there the statistics are starkest, more quenched disks, more thin airs, more oxidized skies. The central engines choreograph the exceptions. When an accreting nucleus flares, a pencil of hard light traces a corridor of exaggerated loss. When it sleeps, planetary erosion returns to the dull arithmetic of mean fluxes and compressed astrospheres. Over a gigayear a solar system may traverse cones and shadows several times, and a desert planet's rock will remember the cadence as bands of chemistry layered like pages. Observationally, the test is a census rather than a portrait. Take temperate planets in projection against a stripped wake and stack their spectra. Water bands should weaken relative to CO2 and O4, and helium at 1083 nanometers should deepen for close-in subneptunes. Sort by cluster-centric distance and the dryness should ease with radius. Cross-match with tracers of recent stripping, H-alpha beads and tails, truncated gas disks, hard UV fields, and the bias toward dust-dominated phase curves and strong day-night contrasts should sharpen. Polarimetry ought to find steeper blue slopes where fine dust rules. Time domain data should catch storm seasons that ignore orbital phase and obey dusty feedbacks instead. Direct imaging with next-generation coronagraphs will map continents that are too steady and too bright, lacking the specular hints that seas scatter. None of these signals alone convicts a world of being a desert by cluster weather, but together, mapped onto the galaxy's own scars, they make a verdict. There are countercurrents worth savoring. Gas fountains from halos that were not fully erased can condense as thermal rain and briefly repaint rings with star formation, softening radiation fields and dribbling fresh comets inward. Giant planets, if present, can serve as volatile accountants, shepherding what remains of an outer belt, swapping angular momentum to flick water-rich bodies sunward on schedules civilization could exploit. Tidally heated moons keep oceans under ice even as their skies sandblast away. Rogue planets shaken loose by tides become cold archives where atmospheres collapse as snows and keep, in layered ices, a chemical history more faithful than any weathered rock. Even dust can become an ally. Engineered lofting of larger grains during peak storm seasons can push microphysics toward faster settling and clear windows for light and warmth to reach ground. From a surface, the phenomenology is intimate. Noon light has weight, it presses without heat when dust aloft inverts the lapse rate. Shadows are soft-edged, the sun's disk pales to a brass coin long before it sets, the stars come late and weak. A storm announces itself not with thunderheads but with a slow loss of distance as the world turns sepia. Static prickles on skin because the air is poor at discharging, nearby rocks tick with tiny sparks in the dark. If mountains exist, they wear aprons of dunes that creep uphill in rare, violent gusts and slide down in long, sighing avalanches. In the lee of any obstacle, you find a lens of fines, silky and treacherous. Underfoot, crust breaks into polygon plates with rims white from salts that have wicked upward and crystallized. Your breath would taste metal if you could breathe it at all, instruments would foul, optics would film, filters would clog and then tear, yet chemistry kits would be happy, because the air is honest about what it has lost. On the scale of galactic evolution, jellyfish episodes are punctuation marks in long sentences about supply chains. Filaments that once poured cold gas along cosmic scaffolding into halos find their way interrupted by hot atmospheres and crowding neighbors. The grammar shifts from clauses about growth to ones about allocation. The planets inside those sentences inherit the edit. Where supply is steady, climates can meander and recover. Where it is cut, they ratchet toward aridity with only small backsteps allowed by volcanism and luck. Read enough spectra, and you can tell which paragraph a world belongs to without seeing the galaxy at all. Read the galaxy, and you can guess, within odds, the color of its planet's dunes. If intelligence emerges early in that arc, the survival manual will read like a weather book. Build shields upstream in plasma, not only shade downstream in light. Treat comets as reservoirs, not events. Pipe volatiles the way rivers once did, turn crater shadows into cisterns and valley floors into closed basins with recycled skies under transparent roofs. Fold dust into architecture instead of fighting it, use it for radiation mass, for thermal lag, for controlled scattering that lengthens day when needed and shortens it when not. Calibrate expectations to teleconnections that run from cluster shocks to your barometer. Understand that deserts are not only endings but platforms, stable, predictable, stingy but generous in sunlight, manageable once their feedbacks are domesticated. On such worlds the horizon is not a line where water meets sky, it is a ledger, and every dune crest is an entry that balances gravity, pressure, and time. Eventually the deserts begin to inherit the stars. When a galaxy sheds its gas, the asymptotic giants it already minted take their turn as weather makers. Slow winds from bloated elders bleed carbon dust, silicates, and S-process crumbs into an environment that can no longer turn those gifts into clouds. The grains drift as free agents, not seeds for rain. They redden starlight along tangents and lay thin, photochemically active films on exposed rocks, catalyzing halogen cycles in sunlight that is now harder, more ultraviolet than the skies their ancestors knew. Micrometeoroid fluxes rise as cluster tides and harassment stir loose debris. The thin air offers little break, so small impacts become hot pinpricks that weld glassy skins onto dunes and melt dark varnishes on bedrock. Over thousands of seasons the upper centimeters of regolith evolve into a laminated archive of sparks and dust, each layer a tally of storms, impacts, and chemistry accomplished without rivers. Climate models for these worlds converge on a few attractors. With little water to set a moist adiabat, lapse rates skew toward dry limits, inversions and dust layers decouple the boundary layer from free air. The diurnal cycle is governed by radiative time constants of aerosols rather than by latent heat. Albedo, dust feedbacks carve two basins of behavior, bright, thin air states with strong day-night contrasts and deep, dust-loaded states where the sky glows and the surface cools, a kind of anti-greenhouse that stalls convection while keeping the middle atmosphere warm. Transitions between them are triggered by thresholds in wind stress and particle size distributions, so the timing is chaotic, with multi-year plateaus punctuated by abrupt flips. If oceans ever existed, the shoreline fossilizes as a reflective ring that modulates planetary light curves. Spectroscopy of those rims would show evaporite suites ranked by solubility, carbonates low, then sulfates, then chlorides, while the isotopes climb like stair treads, D/H high, (18O/16O enriched, noble gases stripped in mass order. Photochemistry rewrites the palette. With water lines faint, CO2 becomes the dominant infrared narrator, its 4.3 and 15 micrometers bands deep and squared off by pressure. Oxygen dimers mark the visible and near-infrared at 0.63, 1.06, and 1.27 micrometers, but the triad is a memorial, not a breath. Ozone appears in a precarious column that swells under strong UV only to be cored by particle events, sulfur oxides fed by volcanism and dry lightning seed aerosols with wide, blue-sloping scattering that steals contrast from reflected light maps. Trace CO lingers because nothing wet remains to finish oxidation. Nitric acid forms on dust and waits for a rain that never comes. Where chlorine finds perchlorates in sunlit films, it cycles with oxygen in reactions that proceed in salty brines for minutes at dawn and freeze into silence by noon. If biology ever touched this chemistry, its signatures would be subtle, fractionations in sulfur around evaporite margins, organics trapped in halite like tiny time capsules, signals that survive only because the environment is so still. The neighborhoods that birth jellyfish are not uniform wind tunnels, they are patchworks of fronts and relic shocks, mini-halos and cavities inflated by old radio lobes. A solar system's path through this quilt changes the punctuation of loss. Cross a cold front and the ram pressure can double, step into an ionization cone and particles spike by a factor of 10, slide into a shadowed eddy behind a subcluster and the environment softens for a few million years. Over one galactic year the cumulative exposure matters more than any one squall, yet rocks remember squalls, glass spherules aligned with a wind that blew for a century, nitrate spikes layered between dust beds, a band where helium escape heated the exobase and etched its signature into the helium triplet that a telescope, centuries later, will read as a flare in a transit light curve. Giant planets modulate fate like valves in a pipe. A massive neighbor can corral what remains of an outer belt into resonances that drip water-rich bodies inward on long, predictable periods. It can also eject them wholesale when the stellar neighborhood jostles, trading a drizzle for a drought. Where belts survive in shards, bombardment delivers pulses of heat and trace volatiles that briefly sag dust feedbacks and carve dark streaks after storms, then vanish back into the thin air. Tidally heated moons, meanwhile, keep private weather under ice, circulating brines with minerals that encode pressure, temperature, and radiation as cleanly as any atmosphere. In caves and fractures, chemistries learned from Earth's Atacama and Antarctic dry valleys would hold out, perchlorate reducers, sulfur cyclers, organisms that treat humidity like a harvest and sleep until it returns. From a telescope seat the program is straightforward and grand. Map jellyfish tails and hard radiation fields across clusters, sort transiting planets by projected position along those scars, stack spectra with care. Expect helium 1083 nanometers absorption to deepen near strong EUV corridors for close-in sub-Neptunes. Expect O4 to correlate with suppressed H2O in temperate candidates projected against wakes. Expect polarimetric slopes to steepen where fine dust rules. Watch phase curves for dust season hysteresis, not orbital phase coherence. Look for continents that are too steady and for the missing knife-edge glint of seas. Use millimeter eyes to weigh dust in exospheres and wakes. Use X-ray maps to chart the headwinds. Fold it all into a joint inference that treats galaxies and planets as one weather system. None of this renders hope quaint. Scarcity is a design prompt. On a dry world a civilization would edit the radiative budget with mirrors and veils, not just shades. It would swell magnetospheres upstream with current loops, not only huddle beneath domes. It would treat comets as cisterns and crater shadows as reservoirs, piping volatiles through buried conduits to closed basins roofed by transparent films that hold the local sky at a few tens of millibars. It would time dust with seeding, launching larger grains during peak storm thresholds to bias microphysics toward fast settling in open windows for agriculture that drinks from recycled brines. It would use the thin air as mass for radiation shielding and thermal lag in architecture, walls that glow at dusk because they have stored the day. Most of all it would read teleconnections, learning to forecast not just its stars' moods but the clusters, and to schedule life against shocks it cannot soften. In the end the analogy remains tight. A galaxy that grew streamers under pressure is a ledger of supply interrupted, a planet that turned to desert is that ledger paid in local currency. The same inequality, external force over internal hold, drives gas from disks and water from skies. Where the quotient dips below unity, tails retract and rains might return in trickles. Where it climbs, the streamers lengthen and dunes advance. The science is an equation, the vista is a copper horizon under a redder sun. The lesson is practical. Climate, at any scale, is logistics, and logistics can be mapped, predicted, sometimes repaired. Read the tentacles, and you read the fate of seas. There is a second ledger written not in light but in spin. Dust and rock grains tumbling through thin air align with magnetic fields that thread both the planetary boundary layer and the larger intracluster wind. Their preferred orientations polarize scattered sunlight and inscribe a weak, rotating signature that follows the field more than the weather. Over seasons the pattern drifts as the heliospheric nose precesses under external pressure. Over millennia it wobbles with the star's motion through patches of denser plasma. A remote observer reading those polarization angles against time could back out the geometry of both the planet's field and the headwind that squeezes it, an inverse barometer from glints. In the subsurface, remnant magnetization captures storm epochs as stripes. Dust-laden gust fronts carry charged fines that settle into layers whose magnetic textures differ from calm-air deposits. Drill a core and you would hold a barcode of wind and field, a palimpsest where every stripe is a gust and every reversal a squall written by plasma far beyond the sky. The mechanics of loss also change with altitude in ways that matter for spectra. In rarefied, oxidizing atmospheres the homopause sinks, molecular weights stratify earlier, eddy diffusion weakens while molecular diffusion takes over, letting light species climb with fewer collisions. Exospheres fatten and adopt comet-like geometries, especially around small planets with hot day sites. Helium becomes the storyteller because it is both abundant in the mantle and honest about heating. The metastable triplet at 1083 nanometers deepens when EUV is high and magnetospheric compression opens particle routes. Hydrogen, when present at all, paints Lyman alpha wings that telescopes must peel from the interstellar foreground. Deuterium tells you the history of escape if you can catch it. Oxygen does not merely remain, it polymerizes into O2 collision pairs and feeds an ozone layer whose thickness jitters with particle weather, a flicker you can time against the heartbeat of an active nucleus or a passage through a cluster cold front. Geography builds its own statistics. Without rainfall to erase relief, dunes and yardongs inherit prevailing winds and preserve them as macro-scale compasses. On basin floors, evaporite polygons grow to hundreds of meters across, their edges heightened by capillary wicking that lifts brines and leaves salts at rims. In thermal IR those rims glow at dusk because crystals hold heat longer than dust. In reflected light they redden and brighten the landscape enough to write shallow, broad features into disintegrated phase curves. Over lava plains, thin films of desert varnish mature under UV and dust, darkening spectra in the red and near IR without the water-related absorptions that biogenic varnishes on wetter worlds would show. Where volcanism continues, gases erupt into thin skies and condense as exotic frosts. SO2 turns to bright hoarfrost in crater shadows only to sublimate by noon, an albedo transient large enough to modulate the light curve for days. Each process is a punctuation mark a telescope can hear if it listens long. Galaxies add their cadence. Subcluster mergers launch sound waves and shocks that ring the intracluster medium. As those arcs pass, the headwind's density, temperature, and bulk speed all change at once. A star system that happens to be near pericenter when a shock arrives experiences a compounded season, RAM pressure peaks, EUV fields harden, and particle backgrounds spike. Transit spectra taken during such episodes would show an atmosphere in a breathing mode, helium lines deep, sodium absent, water flat, before relaxing toward its baseline. Stack many systems by position angle around a jellyfish wake and the variability should synchronize with X-ray surface brightness edges and radio relics. It is multi-messenger climatology. Use X-rays to see the wind, radio to see the fossil lobes and draping fields, optical/IR to see the deserts that wind and fields create. There are chemical tricks that make deserts look briefly wet from a distance. Brine films in morning shade can grow microns thick and survive minutes before evaporating. They deepen faint absorption near 3 micrometers and add a whisper at 6 micrometers that could be mistaken for water vapor if time averaged. Chlorine chemistry builds perchlorates that, when illuminated, release oxygen and trace chlorine oxides, confusing ozone retrievals unless spectra are taken at multiple phases and tracked for particle events. CO lingers alongside O2 because the usual wet oxidation partners are missing. Interpret O2 plus CO together without context and you might claim metabolism. The antidote is ensemble context. Worlds projected against fresh tails should bias dry, those beyond the caustics of ionization cones should wobble less, those in backswirls behind subclusters should show slower loss and weaker O4. No single spectrum suffices, the paragraph matters. Buried waters and gases complicate the surface's finality. Serpentinization in ultramafic rocks keeps hydrogen trickling where heat and fractures allow, and with it a chemistry that can knit organics out of CO2 even when skies are thin. Clathrates archive past atmospheres under permafrost lids, thaw lines, if geology or impacts breach them, can exhale bursts of methane into air that is otherwise poor in reducing gases. Those puffs write transient signatures at 3.3 micrometers and in millimeter bands. They fade quickly under UV but recur with seasons of geologic stress rather than solar illumination. In caves, even thin humidity cycles leave concretions of halite and thenardite that grow like hour markers, trapping organics and noble gases in inclusions. If anyone someday reads them, the inclusions will recount the atmosphere's retreat in fluent isotopes and the pulse of particle weather as argon ratios and neon fractionation. Engineering, if it appears, would aim where physics least resists. Particle shielding upstream, current loops and plasma sails positioned sunward, changes ion pickup rates more efficiently than thickening domes can change photolysis below. Radiative editing uses angled mirrors to bias the diurnal cycle, lengthening gentle mornings when brines can be useful and compressing harsh noons when dust feedbacks run away. Microphysical tuning seeds larger grains ahead of storm thresholds to hasten settling and break the positive loop between lofted fines and atmospheric heating. Logistics reimports volatiles from cold traps and dark craters as if piping a second atmosphere through the crust, closing water loops inside roofed basins held at tens to hundreds of millibars, pressure enough for liquid, low enough to keep structures light. The greatest expense is knowledge, forecasting teleconnections from cluster shocks to local barometers well enough to plan agriculture, travel, and maintenance cycles in a sky that answers to two weathers. Time does not stop simply because rain does. Red giants fade, white dwarfs inherit neighborhoods that their progenitors helped desiccate, planetary systems settle into long afternoons under cooler suns. Deserts stabilize into quasi-steady states where dust seasons flip between two attractors with low-frequency beats set by orbital precession and storm thresholds. If halos drizzle a little gas back into the galactic disk, the radiation field softens, and a planet with residual outgassing can thicken its air from threadbare to merely thin. If comet herds survive in resonances, late trains of impacts can write dark streaks across bright evaporite rings and briefly push climates across condensation points inside domes. None of this rebuilds oceans by itself, but it shifts odds and lengthens patience, the two currencies that matter after supply chains have been cut. From such a world the sky at night is still an education. Jellyfish streamers hang as ghostly highways where new clusters twinkle, a reminder that even as one place starves another feasts. The constellations shift with the galaxy's slow bounce through the cluster's lanes, radio auroras crackle along magnetospheric ovals tightened by the wind, meteors are frequent and shallow because the air is thin, leaving more glass than ash. A traveler who knows how to read light would see, in every copper sunset and long twilight, the arithmetic that tied a galaxy's tentacles to a planet's dunes. A telescope that knows how to average would see, in every stacked spectrum, that same arithmetic written across dozens of worlds. And a civilization that learns the lesson would treat climate as logistics from the start, budgeting not only heat and light but also the quieter currencies of shielding, grain size, and patience, so that when the headwind rises and the pantry runs low, the ledger still balances long enough for seeds to take in a place where rain no longer comes. Instrumentally, the cleanest discriminants live where environments couple. Low-frequency radio should catch cyclotron, maser emission from magnetospheres squeezed by high external pressure. The cutoff tracks the planet's field strength, and the burst rate rises when solar wind proxies spike, so a cluster headwind that compresses astrospheres should brighten exo-auroras into the tens to hundreds of MJY at tens of megahertz for the most favorable hot, fast rotators. Millimeter spectroscopy can weigh dust in exospheres and wakes, with continuum bumps at 0.8 to 3 mm tracing micron, sub-micron grains lofted from dry soils. Cross-correlation with stellar radial velocity jitter separates planetary dust from stellar activity. High-resolution optical/IR transmission spectra resolve line cores to read winds and scale heights directly. Sodium D and potassium at 770 nanometers track ionization fronts, while the helium 1083 nanometers triplet maps energy deposition and outflow geometry with Doppler-resolved tails. Polarimetry constrains microphysics. A steep blue slope flags fine silicates, a flatter one suggests sulfates, and phase-dependent swings reveal particle growth after engineered seeding or natural coalescence. Stack all of this by cluster-centric distance and along X-ray edges and radio relics, and the ensemble resolves into an environmental sequence rather than a field star scatter plot. Dynamics adds another lever. Tides and flybys in crowded infall groups pump eccentricities and inclinations, imposing climate cycles that ride atop desiccation. Eccentric orbits push perihelion insolation spikes through thin skies that cannot buffer heat, yielding asymmetric phase curves and seasonal helium surges as exobases expand. Inclined orbits tilt dust circulation cells, biasing dune migration and building hemispheric albedo dichotomies that persist for millennia. Giant planets act as governors or saboteurs. Mild resonant migration can feed inward trickles of icy bodies on secular timescales, while close encounters can clear belts entirely, shutting down late-stage hydration. In the statistics that means desert indicators should anti-correlate with stable long-period giants but correlate with systems showing hot Jupiter migration scars and eccentric inner architectures, a demographic fingerprint that large surveys can test. Laboratory and field work close the calibration loop. Beamlines and plasma chambers measure sputtering yields and triboelectric charging for analog dust under UV and particle fluxes matched to cluster cones. Thermal vacuum rigs quantify evaporation and salt crust growth rates in brines that last minutes at millibars. Flow tunnels in dry air map saltation thresholds as functions of grain size, charge, and pressure to feed GCM microphysics. On Earth, the Atacama, McMurdo Dry Valleys, and high Andes salas provide natural laboratories where perchlorate chemistry, nitrate deposition without rain, and halide inclusions preserve organics and noble gases in ways directly portable to retrieval models. Fold those constants into radiative, convective models coupled to escape physics, and the forward problem, spectra, light curves, polarimetry, lands in a region of parameter space narrow enough to invert for dryness with confidence once environmental priors from X-ray and radio maps are applied. Formation does not fully cease in stripped wakes, and that nuance matters. Star-forming beads along jellyfish tails host protoplanetary disks in harsher baths than typical H2 regions. Disk lifetimes shrink, outer radii truncate, and dust growth races against photoevaporation. The survivors skew toward compact, rocky systems with meager volatile budgets and early atmospheres pre-eroded by EUV, essentially pre-desert worlds. If any sub-Neptunes form, they do so late and close in, primed for rapid envelope loss that accelerates under cluster conditions. That production function predicts a higher fraction of bare, high-density planets near active tails, a shift observable through mass, radius statistics and helium demographics. Conversely, backsplash regions where halos drizzle a little gas back into disks soften the radiation field and widen the disk survival window, seeding modest rewetting by late comets and slightly thicker skies, a second-order effect, but one that should appear as a gentle radial gradient in waterband depth outside the core. Even the biochemistry of false positives sharpens with context. O2 alongside CO and a strong O4 triad, with muted H2O and variable O3 tied to particle weather, flags oxidation by loss rather than metabolism. Add perchlorate photochemistry and you get day, night oxygen flicker uncorrelated with seasons. A signature biology is unlikely to mimic at low pressure. Methane bursts that recur with tectonic stress or thaw lines but decay on photochemical timescales point to clathrates or serpentinization rather than cows. Sulfur isotopes near evaporite margins can bias by a few per mil in patterns opposite those expected from robust microbial cycling, and noble gas fractionation, 36 AR down, 38 AR up, anchors the escape history independent of chemistry. The solution is an observing strategy that is boring by design, multi-epoch, multi-band, cross-matched to environmental maps, patient enough to watch dust seasons flip and particle weather pulse, comparative enough to let ensembles speak where single worlds can deceive. If agency enters the scene, the easiest wins are upstream and microscopic. Plasma shield stations sunward to inflate magnetospheres cut ion pickup more for the same what than any dome could. Angled mirrors adjust local radiative budgets at dawn and dusk to lengthen the brief windows when brines are liquid. Grain size engineering nudges storms toward faster settling, opening clear sky slots on schedules set by forecasts that ingest cluster shocks as boundary conditions. Logistics treats volatiles as infrastructure. Comet farms tended in resonant corrals, pipelines from crater shadows to roofed basins that hold a local sky at tens to hundreds of millibars, electrolysis and Sabatier loops running on sunlight that deserts generously supply. None of this rebuilds an ocean, but it stretches hydrological half-lives, stabilizes agriculture, and buys time, an honest currency in a place where a galaxy's tentacles once wrote, insufficient funds, across the sky. Detection can lean on background beacons as much as on the planets themselves. Place a bright quasar or cluster BCG behind a desert world and the tenuous exosphere becomes a foreground etching, narrow, time-variable absorption in Na-D, K, and metastable. He rides on the lamp spectrum as the planet's orbital motion Doppler shifts the lines through rest. Repeat the experiment along a jellyfish tail and the column densities should rise where EUV corridors harden, move off the wake and the signatures relax. Starlight occultations by thin, dusty halos, exospheres swollen by sputtering and micro-impacts, make shallow, chromatic dimmings that last longer than transits and recur with the planet's season rather than its period. Even without a transit, rotational mapping can find deserts indirectly. Stable, high-albedo continents and broad dust belts produce power at low spherical harmonics that refuses to decorrelate with time the way oceans do. Interiors keep a slow conversation with skies that no longer listen. Mantle oxidation states drift as hydrogen escapes and the crust warehouses oxygen. Outgassed species shift toward CO2, SO2, and CO, throttled by redox buffers rather than by rain. Basalts erupt into thin air and quench into glass whose hydration spikes only during rare, cool dawns. The glass then dehydrates, locking a humidity curve into mid-IR features that would look like weak shoulders near 3 micrometers to a patient telescope. Seismicity under low load produces dust fountains when fractures open, a coupling between tectonics and weather that writes episodic brightening into phase curves months after the quakes themselves. Where ultramafic rocks meet water in deep crustal pockets, serpentinization keeps hydrogen trickling upward. The trickle is small, but in thin air it is enough to paint fleeting methane flares that a spectrograph can catch if it is disciplined about cadence. Landscape evolution in these climates runs on thresholds. Once grain-size distributions tip below a critical diameter, saltation becomes self-sustaining. Dunes encroach on uplands and bury paleo-shorelines like pages interleaved into a thicker book. Yardungs carve along bedding plains until a single storm season under unusually high winds collapses entire fins and resets topography in a year rather than a millennium. Evaporite polygons, fed by capillary rise from brines meters below, coarsen as stress concentrates at rims, crack patterns propagate like slow lightning across basins, creating kilometer-scale rings that store thermal inertia and act as passive timekeepers in thermal IR. The rare hydrologic pulses, impact melts, brief aquifer discharges after quakes, volcanic snowfalls on cold plateaus, leave overprinted chemistries in halos around vents and craters, bullseyes a retrieval pipeline can learn to recognize as the fingerprints of accidents rather than climate. On galactic scales, the stopping time for star formation and the drawdown time for planetary water need not match, yet they rhyme. Disks quench over a few times 10 years as inflows are cut and reservoirs stripped, planets pace the decline with photochemical loss, non-thermal escape, and the exhaustion of late volatile delivery. Infalling groups pre-process both ledgers, thinning gas and stirring orbits before the main cluster wind does its work. Backsplash orbits offer temporary reprieves, the headwind eases, AGN cones are crossed less frequently, and halos can drizzle cold clumps back onto anemic disks, conditions that soften radiation fields and lengthen atmospheric half-lives by factors of a few. The aggregate effect, measured with a large enough sample, should appear as a gentle outer rise in waterband incidence and a fall in O4 strength even before you leave the virial radius. Instrumentation earns its keep by being boring and relentless. Multi-epoch transmission spectra across dust seasons prevent brine film mirages from masquerading as humidity. High-resolution line profiles track outflow velocities and separate thermally driven escape from ion pickup by their Doppler shapes. Simultaneous X-ray and radio maps set priors on EUV and particle flux so retrievals do not hunt ghosts. Polarimetry at a handful of well-chosen phases distinguishes fine silicates from sulfates by slope alone. Thermal phase curves captured over years map the flips between the bright thin and dust-loaded attractors. Millimeter photometry weighs exospheres and sifts out planetary dust from stellar granulation via cross-correlation with radial velocity jitter. None of these data singly clinch dryness. Taken together, especially when stacked along jellyfish wakes and across cluster-centric annuli, they turn anecdotes into a climate atlas. If mines inhabit such latitudes, their engineering will look like weather control scaled to thrift. Plasma mirrors and current loop stations sunward swell magnetospheres and cut non-thermal loss by orders of magnitude with power budgets modest compared to doming continents. Heliostat arrays bias mornings longer and noons shorter inside roofed basins, stretching the liquid window for agriculture that drinks brines and returns them with minimal fractionation. Grain size management, seeding larger particles upwind before threshold winds arrive, short circuits runaway dust seasons and opens clear sky lanes on schedules tied to forecasts that ingest cluster shocks as boundary conditions. Logistics treats volatiles like infrastructure, comet corrals maintained in resonances, cryopipelines from crater shadows, electrolysis loops powered by a sun that deserts reflect generously. Oceans do not return, but half-lives lengthen, yields stabilize, and culture learns to read the teleconnections that made their skies stingy. There are edge signatures worth anticipating because they sharpen the story where it frays. Thin, oxygen-rich atmospheres with perchlorate chemistry can generate day-night O2 flicker uncorrelated with seasons, a behavior unlikely for photosynthesis and easy to flag with cadence. Sulfur aerosol loads that rise after particle events but not after temperature swings point to dry lightning and volcanism rather than biology. Noble gas ratios, 36 AR depleted relative to 38 AR, neon fractionated in mass order, anchor escape histories that photometry cannot fake. Stack these against a map of H-alpha beads in jellyfish tails, X-ray pressure jumps at cold fronts, and radio relics marking old shocks, and the ensemble coherence becomes difficult to explain with anything but weather that runs from kiloparsecs down to dune crests. Even the failures teach. A survey that finds no trend in waterband suppression with cluster-centric distance may be sampling backsplash populations that have already recovered some shielding, a null result in helium near strong EUV corridors could indicate widespread giant planet guardians that kept sub-Neptunes at bay, shifting the production function toward high-density worlds. Disagreements between polarimetric slopes and thermal phase curves may betray engineered grain size control rather than nature, an audacious but testable hypothesis if changes correlate with local calendars. The point is not merely prediction, it is diagnosis in the wild, with enough patience to let the environment reveal whether deserts are destiny or design. At night, under copper skies, the connection still feels visceral. The same inequality that pulled gas from a disk, external push over internal hold, etched polygon cracks at your feet and thinned the breath in your lungs. The tails that once shone like jellyfish across the cluster were not ornaments but receipts, itemizing losses that cascaded from galaxies to grains. Read them well enough and you can forecast the color of a horizon on a world you will never walk, infer the chemistry of an air you will never breathe, and decide, early, while there is still margin, whether to build shields, mirrors, cisterns, and patience. In that sense, a desert planet is not a failure state, it is a syllabus, and the class it teaches begins with logistics and ends, if its students are stubborn, with rain made to order beneath a local, human sky. Models that let the physics speak sort deserts into a few durable archetypes rather than a blur. Thin air deserts are the Mars analogs writ large, surface pressures below a few tens of millibars, strong day-night contrasts, dust that sets both color and climate, and escape dominated by particles and heating at the exobase. Pressure deserts sit on the other side of the valley, super-Earths with many bars of dry CO2 that move heat efficiently but cannot cycle water, where lapse rates hug the dry adiabat and clouds, when they exist, are sulfate hazes and lofted fines, not rainmakers. Anti-greenhouse deserts are sky-thick but light-poor, aerosol layers warm the middle atmosphere and cool the ground, locking convection and stretching twilight, the surface lives under a bright ceiling and a cold floor. Brine pocket deserts stitch local exceptions into an arid rule, capillary films at dawn, cave drip points, crater shadow hoarfrosts that briefly melt and refreeze, microclimates that do chemistry for minutes at a time and then go silent for weeks. Each archetype has spectral tells, thin air worlds sharpen thermal phase curves and flatten water bands, pressure deserts square off CO2 at 4.3 and 15 micrometers and grow conspicuous O4, anti-greenhouse states redden polarimetric slopes with fine sulfates, brine pocket planets whisper at 3 and 6 micrometers on a cadence set by dawn and shade. Star type nudges these families along different tracks. Around cool dwarfs, EUV is persistent and flare-spiky, tidally locked geometries compress climate into a dayside kiln and a nightside freezer, with terminator bands that act as valves. Helium 1083 nanometers often dominates the leakage story there, and O3 is jittery because particle weather punches holes as fast as photochemistry can stitch them. F and G-type hosts give steadier UV but larger habitable zones. Planets run cooler at the same stellar flux and can preserve thicker skins longer if supply is not cut. K-dwarfs, long-lived and moderate in UV, are temperamentally kind but not sovereign. Put a K-dwarf system inside a jellyfish wake and the cluster still wins the argument by tightening astrospheres and hardening the background. The neat part is that these differences are testable in ensembles. At fixed cluster-centric distance, dryness indicators should relax in step from M to K to G/F, with caveats where AGN cones slice across the map. Inside multi-planet systems the desert does not arrive evenly. Inner small worlds hit escape thresholds first, sub-Neptunes lose helium-rich coronas until their mass radius points slide into the rocky cloud. Outer terrestrials, if belts survive, hang on longer, especially if a giant shepherds icy rubble into slow inward drizzles. That architecture writes structure into observables, helium tails cluster at short periods, waterband suppression spreads outward with time, dust-driven albedo features decorrelate with orbital phase on inner planets but remain seasonal farther out. Machine learning classifiers trained on simulated retrievals already recover these gradients when fed spectra plus simple environmental priors, X-ray pressure, radio relic proximity. The moral is procedural: do not fit a planet in isolation when a whole family portrait is free for the taking. Timescales keep the ledger honest. Energy limited escape, M tilde operator eta PyR-P3FEUV/GMPK /sim/P-3F_P-Caret3F_P-EUV/GM_PK M tilde operator eta PyR-P3FEUV/GMPK drains light envelopes in tens to hundreds of mir at cluster-boosted EUV, non-thermal channels at a comparable tax when magnetospheres are squeezed. Aeolian reshaping of landscapes runs from hours, dust devils, saltation bursts, to KYR, dune migration, to mir, Yardang sculpting. Photochemical oxidation can flip redox balances in a few mir once hydrogen export outpaces supply. Volcanic outgassing paces out in 1010-year pulses modulated by tectonics and mantle water content. None of these clocks match perfectly, which is why deserts retain texture. A Yardang field can persist under a sky whose chemistry already turned the corner. A world can show helium loss long after its dunes found equilibrium. A brine signature can recur in caves centuries after the last open-air rain. The rock is a faithful witness. Crossbeds and climbing ripples give wind direction and variability statistics. Evaporite sequences rank solubilities, carbonates at the base, then sulfates, then chlorides, while isotope ladders, D/H, caret18O/caret16O, argon and neon pairs, record escape and exchange in mass order. Silica-rich desert varnish grows under UV and dust, darkening near IR slopes without borrowing water features that would betray biology. Impact glass hydrates on cold mornings and dehydrates by noon, riding humidity in mid-IR shoulders that recur with season and microclimate. Cave halides trap bubbles that archive noble gases and trace organics. Read across a depth profile and you reconstruct a century-scale cardiogram of a dying sky. Dynamo physics adds one more hinge. Thin or thick, an atmosphere still modulates core cooling by setting surface heat loss. Deserts, especially thin air ones, can hasten cooling and extend dynamo lifetimes, buying magnetospheric protection even as UV bakes the top of the air. Conversely, pressure deserts insulate. Cores cool slower, dynamos may persist longer still, but the atmosphere's mass loads pick up processes and changes which escape channel dominates. That feedback explains why some thin worlds keep radio-loud auroras while others of similar mass go quiet. Mantle heat, lithosphere thickness, and sky mass form a three-body problem whose solution space has islands of protection and seas of loss. The false wet problem becomes manageable once cadence enters the plan. Morning brine films deepen 3 micrometers absorption for minutes. Perchlorate photolysis toggles O2 and O3 on particle weather timescales. Methane from clathrate burps paints transient 3.3 micrometers features that fade in days. None of these correlate with orbital phase the way oceans and clouds do. A boring schedule, multi-epoch spectra across months, co-observed with X-ray/EUV proxies and radio maps of the wind, unmasks them. Stack by position along X-ray edges and radio relics, and the mirages cancel while climate remains. If agency intervenes, it will exploit the cheapest gradients. Upstream plasma loops that fatten magnetosphere's lower ion pickup with watts that domes could never match. Heliostat fields bias diurnal energy so dawns run longer, when capillary chemistry and agriculture are most forgiving, and noons shorter. Grain size seeding before threshold winds flip a dust season from runaway to self-limiting. Comet corrals and cryopipelines turn reserves in shadow into weather on demand inside roofed basins held at tens to hundreds of millibars. Radiation mass is free in deserts, dust itself, so walls carry sunlight as heat into the night, smoothing extremes for crops that drink recycled brines. None of this conjures an ocean, but it stretches half-lives, and in logistics that is often the whole game. Zoom back to the jellyfish and the analogy tightens again. Tails are public receipts of broken supply chains, deserts are those receipts paid locally. Read the pressure jumps in X-ray maps, the relic arcs in radio, the beads of H-alpha along streamers, and you can forecast spectra: CO2 deep, H2O shy, O42 proud, helium restless. Read enough spectra against those maps and you can forecast landscapes: bright evaporite rings, dunes with steep forward scattering peaks, yardongs aligned with a wind whose direction you measured from a galaxy-scale shock. The environment is continuous from kiloparsecs to centimeters, the diagnosis should be too. And if a traveler were to stand under such a sky, the lessons would feel practical rather than grand. Noon would arrive as a pale coin above a bright ceiling, shadows would blur, static would prickle in the air, dust would taste of iron and salt. Instruments would foul, but ledgers would fill, grain sizes logged, humidity spikes timed, noble gases bottled, spectra taken at dull, disciplined intervals that let the planet confess not in a single dramatic moment, but in the steady arithmetic of loss. The same arithmetic that pulled a galaxy's gas into streamers wrote polygon cracks into the mud at their feet. Learning to read one teaches you to predict the other, and, sometimes, to nudge both toward kinder numbers.